Good day, Doctor. We are Group 3, and today we are going to present our operating system group project. Our project topic is virtual memory management, which are page replacement algorithms, FIFO, and also LRU. So our group consists of 4 members, which are YING, JIAN, and also me, Lin. So I will begin by introducing the operating system concept behind our project. Now I will start my presentation. So as you can see, here is our simulator. So first, modern operating systems need to manage memory efficiently because physical memory or RAM has a limited capacity. However, many applications required more memory than the available RAM. So to solve this problem, operating systems use a technique called virtual memory. Instead of loading an entire program into RAM, virtual memory divides the program into smaller units called page, and only the required page are loaded when they are needed. So whenever a program requests a page that is already stored in RAM, it is called a page hit, and the operating system can access it immediately. However, if the requested page is not currently in RAM, a page fault occurs. The operating system must retrieve the required page from secondary storage before it can continue executing the program. And next, besides explaining the algorithms, we also want to make virtual memory easy to visualize. Therefore, our project uses a real-world analogy which is summarized in this section. But for this session, my teammate will explain this analogy and how it is incorporated into our simulator in more detail. And next, when all the shelf slots or memory frames are occupied, a new page cannot be loaded unless an existing page is removed. Therefore, the operating system must decide which page should be replaced, and this decision is made by a page replacement algorithm. So in our project, we compare two commonly used algorithms, FIFO, which removes the page that has been in memory in the longest, and LRU, which remove the page that has not been used for the longest period of time. So our simulator demo both algorithms side by side so their behaviors can be compared easily. So that's all for my part. I will pass the presentation to my teammate. Thank you.
Good day, Doctor. My name is Qian. So now I'm going to continue our presentation on the real-world scenario and our system design. So first, understanding the page replacement algorithm can be hard, but we always see just a table of numbers. So instead, we've mapped the entire concept onto a library bookshelf, and here is how the analogy works. First, a memory page becomes a book, and the memory frame becomes a slot on the display shelf, and the memory access will be a student requesting for a book. And if the book is already on the shelf, we'll achieve a page hit. And if not, it will be a page fault where the librarian have to fetch it. And if the current shelf is already full, we'll remove an existing book and call it as the victim page. So based on this analogy, we've designed the interface with 3 parts. So first, an input section for the reference string and also the shelf size. 2 shelves running the FIFO, first in, first out, and LRU, least recent use, side by side, based on this identical input, and also some playback control, including the play button, step forward, step back, and also a reset button. So this allows the user to study each decision by each algorithm step by step on the side. So this algorithm is achieved by using a JavaScript function. So here we have the simulated FIFO and also the simulated LRU functions. So both of these functions takes the reference string as also the frame count and replace it step by step. So first, the first in first out uses a plain array as a queue, and on every page fault, we'll remove a book from the shelf which is full by using the mem shift function to remove the book which is the oldest at the index 0, regardless how popular it is. And next, as for the least recent use algorithm, we'll use the same array but with one key difference. So here, at each page hit, we'll remove the book access from its current position and push it to the end of the array using the mem filter and also the mem push. So this will resort the shelf, which is the array, to keep the index 0 to hold the least recently used book. So in short, both of these functions share an almost identical structure, and this will be the only key difference. And that's what produces such a different behavior, as demonstrated by my teammate later. And that's all from me. Thank you.
Good day, Doctor. My name is Lee Jian. Now I'll give the demonstration. I'll use our default test sequence and run it through both FIFO and LRU. First with a small shelf, then a bigger one, so we can see how each algorithm reacts. First, a shelf that holds 3 books. As you can see here, book 1, 2, 3 fill the shelf right away. So when book 4 arrives, FIFO removes book 1. It's been there the longest, regardless of how often it's been asked for. Book 1 get request again, almost immediately. So it fetch all over again. FIFO only tracks when a book arrives, never how often it's used. So this keeps happening. On LRU, the same shelf tracks the last time each book was touched instead. So when book 5 calls a fault, it removes whichever book has gone the longest without being requested. After full trap step sequence, FIFO ends with 9 faults, 3 hits, and a 25% hit ratio. And LRU actually ends slightly worse here, 10 faults, 2 hits, and 70% hit ratio, because this specific sequence is a tough case for a small shelf. Now let's give both algorithms more room, 4 slots instead of 3, and run the exact same sequence again. As you can see here, book 1 to 4 fill all 4 slots. So when book 5 arrives, FIFO removes the book 1 again, since it's still the oldest, and just like before, books 1 gets request again right after. Another fault here, extra shelf space doesn't fix the FIFO core problem, since it still isn't paying attention to how useful a book actually is. Now we'll go to LRU with 4 slots, which behaves differently. With more room, it has more usage history to work with. So when a fault happens, it can make a smarter call about which book has genuinely gone unused the longest. So after 12 steps, with 4 slots, FIFO barely changed. It also 10 faults, 2 hits, and 70% hit ratio. And LRU drops to 8 faults, 4 hits, and a 33% of hit ratio. So here's the pattern across the both runs. Giving LRU more shelf space generally help. It hits ratio double from 70% to 33%. FIFO, on the other hand, barely move, still on 70% right away. That's because FIFO decision only depends on arrival order, not the real usage. So more space doesn't necessarily translate into smarter choice. That's all from me. Thank you.
Good day, doctor. My name is Lao Zhiying. Now I will continue with the Belladis anomaly. Normally, the increase in the memory frames will decrease the number of page faults. However, in some conditions, the increase of the memory frames will also increase the number of page faults. And this is known as Belladis anomaly, which would also happen in first-in, first-out algorithm. So as we can see, with the number of frames 3, the number of page faults is 9 with 3 page hits and the ratio is 25%. If we increase the number of frames to 4, then the number of page faults will increase to 10 with only 2 page hits and the ratio decreases to 17%. So over here, we can see the comparison that the increase of the frames also increase the number of page faults of first-in, first-out algorithm. This is because first-in, first-out algorithm does not consider the frequency of use of an item and just remove the item that stay in the memory for the longest of time. This ignores the real-time utility, and the item that might be frequently used will be removed and causing more page faults to happen. And that's all from me. Thank you.